100% yield and error. This is another thing that stoichiometry allows us to do. We can actually perform experiments and figure out just how efficient we were based on what we should expect to get out of a reaction. So our percent yield is a ratio of actual yield to theoretical yield. So actual is the amount of product that actually forms when the reaction is carried out in the lab. That's your experimental value. So if you perform an experiment, you weigh your product on a scale, that's your actual yield. The theoretical yield is what we're going to find using stoichiometry. That's what we've been calculating. That's the amount you should produce. You usually don't produce the full amount, okay? Organic chemistry, if you ever have to take that, you'll start to get very, very excited when you're getting 25% yields. It's fantastic, okay? But you need to be able to report just how efficient things are. Also, percent yield is important in industry because if we have a higher yield, that means we've wasted less of our precursor. And if there's less waste, that means there's lower cost for products. So this is important. A lot of chemistry goes into making the things that we use every day. So if you want your phone to be as cheap to you as possible, or cheap to the consumer as possible, you want to reduce your percent error. You want to increase your percent yield. Okay? Also, in terms of the environment, we want to make sure that we're using our resources as efficiently as possible. So our percent yield, how we're going to find it, we're going to take the actual yield and divide it by the theoretical yield, and then we're going to multiply that number by 100, okay? Biggest mistake that I see is that people forget to multiply by 100. It's a percent. That means per 100. So you need to multiply that number by 100 to make it a percent. Don't forget to do that. Or if you do, make sure you show your work. Percent error is going to be how much error there is between the actual and the theoretical yield. So how we're going to find that is we're going to take 100 and we're going to just subtract our percent yield. Okay, it's the difference between 100 and the percent yield. So a sample problem that we have. We have 9.8 grams of hydrogen reacting with excess oxygen to produce 85 grams of water according to this equation. What is your theoretical yield, actual yield, percent yield, and percent error? Whoa. Does that seem like a lot of information to get to you? No, I want to continue to be in the presentation. Thank you. I just would like to be able to write on it. So, I agree. That is a lot of information. We got to figure out how to parse it. What is nice is that we can break this down here. So, 9.8 grams of hydrogen reacts with excess oxygen to produce 85 grams of water. Okay, so first I'm going to figure out what these two are going to be used for. Now, since it says to produce 85 grams of water, since it actually produced 85 grams of water, that's going to be our actual yield. Now we have 9.8 grams of hydrogen. Okay, we're going to use that to determine our theoretical yield. Okay, so we're going to draw this little road map that we have here, right? We've got 9.8 grams. We want to figure out grams of water. Okay, grams to moles, moles of hydrogen to moles of water, and then moles to moles. Okay. So let's move over here. We're going to write up our theoretical. So remember, we're starting with 9.8 grams. Actually, I'm going to clean up the rest of it, and now I'm going to 9.8 grams. And I don't want to do that one. I want to do this one. Okay, so we're going to set up our theoretical. We're starting with 9.8 grams of hydrogen. Going from grams of hydrogen to moles of hydrogen. Kicking out the moles of hydrogen to get to moles of water. Then we want to get rid of the moles of water and get to grams. Okay, I'm setting this up kind of quickly because we should be at the point where we're kind of understanding how to get there. Okay, so remember, if I'm going from grams to moles, I want to put 1 with my mole, and with my grams, I'm going to put the molar mass. Okay, I have 2 hydrogens. 1 plus 1 equals 2. Okay, if I'm going from moles of one thing to moles of another, I'm just going to put 2 in there. Or I guess coefficient, so 2 for each of those. And we've got another moles and grams. So I'm going to put 1 with this mole, and then in the grams we're going to put molar mass. Molar mass of water is 18.0 because we have 2 from the hydrogen, 16 from the oxygen. So we're going to multiply across the top and divide by what's on the bottom. So we have 9.8 times 18 divided by, well, I guess, and times 2, but we're also going to divide by 2 on the bottom there. So I'm going to skip over that for now. Okay. If we do that, you should come up with 88.2 grams. Now remember, we said that their actual yield was 85 grams. Okay, then we're going to put our theoretical in here, 88.2, divide those, and then we're going to multiply by 100 to get our percent yield. We have a 96.3% yield, which, if we subtract that from 100, gives us 3.7% error. Okay? Now, just in terms of how you can label things, I am okay with you putting percent capital Y for percent yield, and you can put percent capital E for percent error, and I will know what that means. Okay? Once again, I want you to be as efficient as possible and make things as understandable as possible for me. Okay, let us do another one. Okay, I only have one more left. Okay, so aluminum hydroxide is often present in acids to neutralize stomach acid, which is hydrochloric acid. So if 14 grams of aluminum hydroxide is present in an antacid tablet, determine the theoretical yield of aluminum chloride produced when it reacts with stomach acid. If the actual yield is 22 grams, what's percent yield and percent error? Okay, so they're nice. They told you the actual yield is 22, so we don't have to split that up. We're going to start with 14 grams of aluminum hydroxide. Okay, so we're going to draw out our roadmap, as always. We've got 14 grams of aluminum hydroxide. I want my actual yield of aluminum chloride. Not moles, grams. So we're going to go from grams to moles, over to moles of aluminum chloride, and up to grams. of aluminum chloride. Okay, I am going to give you time to set that up on your own, and then I am going to just pop this up here so you can check your work, because I do want you to get the opportunity to try this on your own. Okay, so checking your work here, okay, make sure we're going from grams of aluminum hydroxide to moles of aluminum hydroxide to moles of aluminum chloride to grams of aluminum chloride. Okay, check and make sure that your molar masses are correct. Okay, and so what we should type into our calculators is going to be 14 times 133.5 divided by 78.0. Okay, what you should get is 24.0 grams of aluminum chloride. Our actual one, if you remember, was 22. Okay, so then we're going to divide that by our theoretical, which is 24, and then multiply that by 100. So we get 91.7% yield. Okay, 100 minus 91.7, right? That's going to be not 9, 8.3% error. Okay. Those are your two example problems for today. Once again, you'll be able to check your work with the assignment that you have today, and you can ask me any questions that you may have. Thank you.